Yes, sir. I can hear you, sir.
Okay, 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 Mark. Thank you, thank you. Okay, in last class, we seen that the third topic of Unit 3, that is fundamental theorem of arithmetic. In the first page, I show some tree diagram. So, in the tree diagram represents what do you mean by fundamental theorem of arithmetic. That is, first I have some integer. That is, that integer can be represented as product of two integers. Again, one of the product again represented as product of two integer and so on. When we stop the procedure, we get the product of prime number. We stop the procedure. This is nothing but fundamental theorem of arithmetic. That is, every integer greater than or equal to 2 is a prime, or it can be expressed as the product of the prime numbers. So this is called fundamental theorem of arithmetic. So I shown yesterday date is from the date the sum of that sum is nothing but a prime number. After that, that is prime numbers nothing but building blocks of all integers and so on. I will explain all these things. This is not important. Okay. The see in last class I gave two lemma, one corollary. After that I will explain one theorem. These three are very important. If you understand the lemma only, then only you can get the clear cut idea in each and every step of the theorem, proof of the theorem. Okay. So that is lemma. First lemma says that if P is a prime number, P divide the product of integers where A and B are integers. Okay, it's understood that A and B are any integer. So P divides the product of past integers. Sorry, A and B are past integers. So P is a prime. P divides a product of two integers. Then definitely either P divides A or P divides B. That means a prime divides a product of two integer. Definitely the prime divides one of the integer. Lemma 2, the prime P divides the product of n positive integers. Definitely prime divides one of the integer, at least one of the integer. In lemma 1, lemma 2, prime divides the product of integer. But lemma 3, that is corollary, there are n plus 1 primes, that is P is a prime, then Q1, Q2, Q1 all are prime. Okay, P divides the product of the n primes. P divides the product of the n primes, then we conclude that P must be equal to any one of the prime. This is most important corollary. You have to understand in clear. Okay, that is that the conclusion is a prime cannot divide the another prime because the only factors of a prime numbers are one and itself. So suppose prime number is divisible by itself alone. So in the left hand side is there is P is a prime, Q1, Q2, Q1 are prime. So suppose we know that this P divides this prime, definitely the prime P must be equal to any one of the n primes. Okay, you have to clearly, you have to understand clearly, prime cannot divide the another prime. Suppose the prime divide the product of the prime, then definitely that prime P should be equal to any one of the prime. Okay. This is an important theorem. The question is state and prove the fundamental of arithmetic. This is a question. State and prove the fundamental theorem of arithmetic. This is a 8 mark question, important question. So only I mentioned the attention symbol. This is every integer n greater than or equal to 2 either is a prime or can be expressed as the product of the primes. The factorization into primes is unique except the order of the factor. Already I explained the second line. That is 2 into 3 into 5 square is equal to 3 into 2 into 5 square. So the order, suppose if you change the order of the primes, the factorization itself unique. You cannot consider 2 into 3 into 5 square is different from 3 into 2 into 5 square. You cannot say that. Okay. So quickly I recall the theorem because this is an important theorem. So, so what I shown in the figure on the first page, that is the procedure for our proof. So first let us prove the every integer n greater than or equal to either a prime can be expressed as the product of primes. So let n is greater than or equal to 2 be an integer. When n is a prime, then it cannot be factored further. Okay, so if n is prime, the theorem is proved. N is not a prime, n can be represented as, because n is not a prime means n is composite. Composite number means at least you have two factors other than one. Okay, so n can be represented as n1 and n2. The range of n1 is n1 and n2 is greater than 1 less than n. So if n is prime, the theorem holds good. N is not a prime, again n can be factorized into n3 into n4. So the value of n3, n4 is greater than 1 and less than n1. So similarly, we can proceed for n2, n3, n4 and so on until n can be expressed as the product of prime numbers. So now I prove the existent part. Now I am going to prove the uniqueness part. Uniqueness part is, suppose n greater than or equal to 2 has two representation of the product of prime. Say you can write in different way, n equal to this. First you can write n equal to this. After that you can write n equal to this. Okay. So n equal to p1, p2, p3, etc. pr. The next line n1 equal to q1, q2, q3, etc. qs. Then both are equal. Okay, the value is equal. Okay. Then suppose in the two representation there is any common factor, just cancel it. Finally, I can conclude that no pi which is equal to with no qi. That is, no pi must be equal to with no qi. Okay, so pi is not equal to qi. So we know that PA is divides P1, P2, P3, etc. PR. That is, PA is nothing but one of the prime in the R prime. So P1, P2, P3, PR, there are R primes. From that R prime, PA is the one of the prime. So can we easily conclude that PA is divides the product. So P1, P2, P3, etc. PR, which is equal to this, So definitely PA divide this, definitely PA divide this. Okay. PA divide this, we conclude that by corollary, PA equal to PA must be equal to any one of the prime. So PA divides the product means by lemma 1. This is prime, you can consider as an integer. By lemma 1, PA divides the product of integer, PA definitely divides the one of the integer. Okay. So now I can use the corollary. So PA divides the product of the n primes. Definitely PA must be equal to one of the prime by previous corollary, not lemma, corollary. So which is contraction, because we assume that PA not equal to Qj. Okay, this is PA equal to Qj is contraction to our assumption PA is not equal to Qj. Okay, that is, by cancelling out the common factor, nothing will be. By cancelling the common factor, nothing will be out. Hence, n has uniquely represented as a product of primes. Okay. Okay, remaining you can easily see that remaining all are problems. Okay, easily you can go through that. So today I am going to start the next. There is one more theorem in the topic of fundamental theorem of arithmetic. That is also another important. Theorem. Okay. So in the fundamental theorem of arithmetic, in the topic we have two important theorem. One is stated through the fundamental theorem of arithmetic. Another one, the next theorem. This is an important 8-mark theorem, because compared to fundamental theorem of arithmetic, this is a little bit longer proof. So only this is an important compared to fundamental theorem of arithmetic. The statement is there are infinitely many primes of the form 4n plus 3. Already we seen one theorem, that is there are infinitely many primes. Already we seen the last second topic. From the second topic, we learned one theorem, that is there are infinitely many primes. Okay. This is another important theorem. There are infinitely many primes of the form 4n plus 3. Here I mentioned that there are infinitely many primes of the form 4n plus 3. Okay. Proof. So obviously by contraction only we can prove the proof. First, I assume that there are only finitely many primes of the form 4n plus 3. I want to prove that there are infinitely many primes of the form 4n plus 3. By contraction, I can assume that there are only finitely many primes of 4n plus 3. Okay. What are the prime? I conclude that there are finitely many prime. What are they? Okay, say P0, P1, P2, etc. Pk. There are 6 plus 1. Sorry, there are k plus 1 primes of the form 4n plus 3. I can assume that there are only k plus 1 primes. Say P0 from P0 to Pk. Okay, there are k plus 1 primes whose form is 4n plus 3. Whose form is 4n plus 3. So what do you mean by P0? P0 is the first prime whose form is 4n plus 3. What is the prime number? First prime whose form is 4n plus 3? 3. When n is 0, 4 into 0 plus 3 become 3. So P0 represent 3 here. So don't bother about the other primes. Only I bother about the first prime, 3. Okay. So first I assume that there are only finite primes of the form 4n plus 3. They are P0, P1, P2, etc. Pk. That means we have k plus 1 primes. P0 is the smallest prime whose form is 4n plus 3. Pk is the largest prime whose form is 4n plus 3. Here I conclude that is understood. P0 is the smallest prime whose form is 4n plus 3. Pk is the largest prime whose form is 4n plus 3. I conclude, I assume two things. There are finitely many primes of the form 4n plus 3. There are k plus 1. K plus is a finite, so k is a finite number. So k plus 1 is, there are finite k plus 1 primes. The smallest prime is P0, the largest prime is Pk. The smallest prime is denoted by 3 because 4n plus 3, when n is 0, you will get 3. Okay. These two things very important. Okay. So now I am going to consider an integer. Okay. Whose form is n equal to 4 times of P1 to Pk plus 3. So here I left out P0. Very you have to understand carefully. So I construct an integer. So the form of the integer is 4n plus 3. Such a way that I have to construct the integer. So here I am going to prove there is one more 4n plus 3 or the 4n plus 3. The one more 4n plus 3 that does not exist. I want to prove that. Otherwise, there is there exists one more prime which is 4n plus 3. I want to prove that. Okay, for that, first I can construct one integer n equal to 4 times of P1, P2, P3, etc. Pk plus 3. So please observe here I left out P0. There is a reason. Okay, I left out P0. From P1 to Pk, I can construct an integer n such a way that 4 times of P1, P2, P3, etc. Pk plus 3. Now easily you know that n has the form 4n plus 3. Okay, easily I can conclude that n has the form 4n plus 3. Clearly n is greater than Pk. Clearly n is greater than Pk because Pk is the largest prime. I construct n is a product of primes including Pk. So definitely n is greater than Pk and also the same form. That means same form is the form of n is 4n plus 3. Okay, clear? Case 1. N itself a prime. I construct integer. I am going to just analyze whether n is which type of number, whether it is prime or composite, because n has the form 4n plus 3, so definitely it is a positive integer. So now I have to analyze whether it is a prime or composite. Okay. If n itself a prime, then n would be the larger than the prime largest prime Pk of the form 4n plus 3. Suppose if we assume n is a prime, means we know that n would be larger than largest prime Pk, because in assumption itself I assume that Pk is the largest prime. But if we assume n is a prime, so definitely it's greater than the largest prime Pk. Okay, so if you assume n is a prime, n would be the larger than the largest prime Pk of the form 4n plus 3, which is contradiction, because initially we assume Pk is the largest prime. Now we can get n is the largest prime. This is a contradiction. So n cannot be a prime. So case 2, n is an composite. N is an composite. Okay, n is composite means, since n is odd, because the form is 4n plus 3, definitely clearly you know that n is an odd number, because 4 times of some number is even plus 3 is odd, so even plus odd again odd, so clearly we know that n is an odd. So we know one theorem, that is every factor of n is of the form 4n plus 1 or 4n plus 3 in odd and integer. That we studied one topic, odd and even integer. In the topic we proved one thing, that is every odd integer can be represented as 4n plus 3 or 4n plus 1. Already we proved this. So since n is odd, definitely the factor of n is of the form 4n plus 3 or 4n plus 1 or 4n plus 3. Okay, either there are, if n is odd means the factor of n, definitely it's either 4n plus 1 or 4n plus 3. Okay, before this theorem I didn't show that one lemma. Okay, I will show this, after that I conclude this. This is that lemma. The product of any two integers of the form 4n plus 1 is also the same form. Easily you can prove that the product of any two integer of the form 4n plus 1 is also the same form. Okay. Okay. So every factor, see, every factor of the form 4n plus 1, then the lemma n would be the same form. That is, suppose n has many factor, each and every factor of n is of the form 4n plus 1. The product of 4n plus 1 is become again 4n plus 1. So n is the same form, that is n has the form 4n plus 1. See, clearly you have to understand n is odd means there are two forms. Okay, either 4n plus 1 or 4n plus 3. Suppose every factor of n is 4n plus 1 form. Okay, if you multiply 4n plus 1 into 4n plus 1, again you will get the same form 4n plus 1. So every factor of n is of the form 4n plus 1. Then by the lemma n would be the same form. Same form is 4n plus 1. But we know that n is the form of 4n plus 3. Okay. So from this I can conclude that, but n is the form of 4n plus 3. So at least one of the prime factor, say p, must be of the form 4n plus 3. That means n is the form 4n plus 3. If you assume that every factor of n is of the form 4n plus 3, become a 4n plus n would be the form of 4n plus 3. Okay, but n is the form of 4n plus 3. So at least one of the factors should be in the form of 4n plus 3. Then only you will get it n has the form 4n plus 3. That factor, that prime factor, I can say p. Okay. So now I conclude that n has the two type of factors. One is 4n plus 1 as well as 4n plus 3. Okay. So I consider one such form 4n plus 3, that is say p. Okay. So I can classify the prime numbers whose form is 4n plus 3. 3 is one case, other than 3 is other case. I can consider two subcases, the form of 4n plus 3 primes, that is the prime number whose form is 4n plus 3, classified into two types. One is 3, another one is other than 3. Okay. Now, subcase 1, I consider the prime, the factor of n. I already assume that the factor of n, the prime factor of n is p. Okay. Now I assume p is equal to 3 because I can classify 4n plus 3 into two form. That is one two type. One is 3, another one other than 3. Okay. Now for first case, I can assume p equal to 3. Okay, p equal to 3 means definitely 3 divides n, because I assume that p is one of the prime factor of m. That prime is considered as 3, so definitely 3 divides n, because 3 is one of the factor of n. Here I assume that. Okay, because the form of p is 4n plus 3. Okay. So 3 divides n. So which implies 3 divides n minus 3 is obviously correct. 3 divides n means I can consider the integer n minus 3. Definitely 3 divides n minus 3 also. Why I choose like this? Because my assumption n equal to 4 times of p1, p2, p3, etc. pk plus 3. If you bring 3 to the left hand side, that is considered as n minus 3. So only I consider n minus 3 here. So 3 divides n, definitely it's divide 3 divides n minus 3, which implies by 1, 3 divides 4 times of p1, p2, pk. So I assume that n has a prime factor of 4n, form 4n plus 3. So that fact is I consider P. There are k plus 1 primes whose form is 4n plus 3. I can consider first case is 3, the remaining cases other than 3. If we assume P equal to 3, P equal to 3, 3 divides n because n has a factor 3. So 3 divides n. 3 divides n means 3 divides n minus 3. 3 divides n minus 3 from 1 because what is our 1?
Okay, plus 3.
What is our equation 1? See, if you bring 3 to the left hand side I have n minus 3. Right hand side 4 times of P1, P2, P3, etc. Pk. Okay. So, so 3 divides 4 times of P1, P2, etc. Pk. So, please observe here this conclusion from equation 1. Okay. When you observe this, 3 divides this product. We know that 3 is a prime number. P1, P2, Pk are also prime number, but P1 is greater than P because P naught is 3. P1, P2, P3, Pk are greater than P naught. Okay. So 3 divides this product mean definitely 3 divides either 4 or at least P divides 3 divides either 4 or P divides any one of the Pi. Okay, because by lemma 1 says that P divides the product of integer, P must be divide any one of the integer. Okay, so here by conclusion 3 divides 4, otherwise you can say that 2 into 2. Okay, P divides 2 or P divides Pi. By lemma, P divides 2 or P divides Pi. Okay, both are impossible. 3 cannot divide 2 as well as 3 cannot divide PA because PA are greater than the P. So PA are primes. So one prime cannot divide the another prime. Okay, by lemma we concluded 3 by 2 3 divides 2 or 3 divides PA, but both are impossible. Okay, case 2. So in case 1 we get the contradiction. That contradiction that P cannot be 3. Okay, P cannot be factor of 3 cannot be factor of n. Subcase 2. P equal to P other than the PA is nothing but other than 3 prime numbers other than 3 whose form is 4n plus 3. Okay. So definitely P divides n. Okay, because P is a factor of n, we assume that one of the factor of n has the form 4n plus 3 say P. So P is a factor of n, that P I can consider PA because we know only k plus 1 primes. Okay, in first case I assume that P equal to 3. The remaining case I can assume P equal to PA. P represent there are k primes P1 to Pk. So P is the one of the factor of n, then P divides n. We assume that P is the one of the factor of n, so P divides n. P divides n means P divides 4 times of P1, P2, Pk because this P is nothing but one of Pi. This is nothing, P is nothing but one of the integer from these k. Okay, so definitely P divides one of the prime. So P divides this product because P lies inside in P1 to Pk. So P divides n, P divides 4 times of P1, P2, Pk. Definitely P divides the difference. That is A divides B, A divides C, A divides the combination of B and C. So P divides n, P divides 4 times of this. Definitely P divides n minus 4 times of P1, P2, Pk. P divides n minus P1, P2, Pk means P divides 3. Okay. P is nothing but there are k primes P1 to Pk. Definitely it cannot divide 3 because 3 is a smaller, P is a bigger. So here also we get one contradiction. Okay. In both cases lead us to a contradiction. So our assumption must be false. Okay. Okay, if we assume P equal to Pi, you will get the one contradiction. In previous case, we assume P equal to 3, we get one contradiction. Why we get contradiction? I can assume P is one of the factor of n, whose form is 4n plus 3. From that assumption only, I can assume P equal to 3, P equal to Pi. Why we get that assumption? That is n, we consider one integer whose form is 4n plus 3. From the construction only, I can get the false. So the construction is possible because we have some k prime numbers. Definitely the construction is possible. So where we get the contradiction? The assumption, that is, we fix that there are only finitely many prime. That assumption is false. Okay. Finally, we conclude that is both cases led to contradiction. So our assumption must be false. Therefore, there are infinite number of primes of the form 4n plus 3. Okay. So please line you have to read at least 2 to 3 times. This is the easiest to prove. Each and everything easily you can understand. Okay. So at least 2 to 3 times you have to read yourself. Definitely, you see, this is easiest one. Okay. Definitely you will get the 8 mark. Okay. This is important theorem. Okay. Up to this, the topic is over. That is fundamental theorem of arithmetic. Okay. Next, we move on to the next topic. That is GCD. GCD means greatest common divisor of GCD means greatest common divisor. Up to this, we covered 3 topics. The first topic is division algorithm. The second topic which I covered, that is prime and composite number. The third topic which I covered, fundamental theorem of arithmetic. The fourth topic is GCD, greatest common divisor. Okay. Okay, first we see that what do you mean by common divisors or common factor. Okay, so these are all known things. So quickly I can explain the definition. A positive integer can be a factor of 2 positive integers. A positive integer can be a factor of 2 positive integers a and b. Such factors are common factors or common divisor of a and b. So the a positive integer can be factor of 2 positive integer a and b. Such factors are called common factor or common divisor. For example, we have 2 integers, say 12 and 18, have the 4 common factor, namely 1, 2, 3, and 6. So the common factors are 12 and 18 are 1, 2, 3, 6. Similarly, if we assume 12 and 25 has exactly one common factor, namely 1. Okay. So in first case, we have 4 common factor. Next case, we have only one common factor, that is nothing but 1. Next, greatest common divisor. The definition, the greatest common divisor is denoted by GCD of 2 integers a and b, not both 0. Not both 0. 0, 0, we cannot able to find. At least one of them is non-zero. Is the largest positive integer that divides both a and b. So you know very well about this. Okay, the greatest common divisor of 2 integers a and b, not both 0, is the largest positive integer that divides both a and b. It's denoted by, this is a new thing. This is denoted by open a bracket a comma b, close the bracket. If you write like this, this is represents GCD of a and b. Okay, so in every place I don't write GCD. So in the place of, if I write bracket, some 2 numbers bracket means that is GCD of those numbers. For example, what is the GCD of 12 and 18? The common factors are already we seen that 1, 2, 3, 6. Out of the common factor, which one is a bigger one, that is called greatest common divisor. So 6 is a common divisor. What about the common divisor of 12 and 25? So only one possible common divisor or common factor. So that is nothing but the greatest common factor. So if you have only one factor, that is only one common factor, that is nothing but our greatest common factor. If you have more than one common factor, out of the common factor, you have to choose the largest one. Similarly, 11 and GCD of 11 and 19 1, GCD of 15 and 25 5. What about the greatest common divisor of 3 and 0? Okay, suppose in general I can say that GCD of a comma 0 is a, because so whatever number you can put here, definitely that number divides 0. 0 by any number 0. So GCD of 3 comma 0 is 0. In general, GCD of a comma 0 is a is non-zero. We seen some notes. So what I said now, that is GCD of a comma 0 is a, where a is non-zero. One thing you have to clearly understand, please listen. This is a main notation. Please listen carefully. GCD of A comma minus B or GCD of minus A comma B or GCD of minus A comma minus B, for these three cases are out of GCD of A comma B. Suppose we have four cases. All the four cases we assume only two positive integer. This is equal to minus A comma. Suppose you want to find the GCD of A comma minus B, that is nothing but GCD of A comma B. Suppose you want to find the GCD of minus A comma B, that is nothing but GCD of A comma B. Suppose you want to find the GCD of minus A comma minus B, that is nothing but GCD of A comma B. Suppose in the problem, suppose you have minus symbol, so remove a minus symbol and then find the GCD, that is nothing but greatest common factor. Definitely the greatest common factor is greater than 0. The another observation, the greatest common divisor of A and B must be greater than 0. We can confine our discussion of the GCD of positive integers. For example, 3 comma 0, just first note, A comma 0 is here. So 3 comma 0 is 3. So 3 comma minus 2 or minus 3 comma 12, so 3 comma minus 12, which is equal to minus 3 comma 12, which is equal to minus 3 comma minus 12. There is nothing but GCD of 3 comma 12, which is equal to 4. Okay. A symbolic definition of GCD. A positive integer D is an GCD of two positive integer A and B if the first condition is D divides A and D divides B, and if suppose some other number other than D, say D dash divide A, D dash divide B, then definitely D dash which is less than or equal to D. D dash either equal to D or D dash should be less than D, where D dash is also a positive integer. Thus, D is nothing but GCD of A and B. So, what is the GCD of A and B? D divides the both A and B. Suppose any other number divides both A and B, that number should be less than the D, less than or equal to D. Okay, this is the symbolic definition of GCD. D must be common factor of A and B. D must be the largest common factor of A and B. In other words, any other common factor D must be less than or equal to D. This is another definition, a simple definition for 2 marks. The GCD of n greater than or equal to 2 positive integers, that is A1, An up to A1 to An are, there are positive integer which is greater than or equal to 2. Is the largest positive integer that divides the each A. Suppose I want to find the GCD of A1, A2, etc. An. Suppose I want to find the GCD of n integers, there is nothing but GCD of n integer, that is nothing but largest positive integer that divides each A. Each A, there is one less than or equal to less than n. It is denoted by open bracket A1, A2, etc. An. Okay. For example, suppose I want to find the GCD of 10, 25, 30. Okay, out of, you have to check all the that is a common factors of all the three. Then from the common factor, I have to collect the largest one. That's all. The technique is same as GCD of 2 integer. This is GCD of 3 integer. That is nothing but find the common factors for 3 integers. Suppose you have more than one common factor, choose the largest positive integer or largest positive factor. So out of this, only one common. There are 2 common factor. One is 1, another one is 5. So 5 is the largest common factor. Therefore, GCD of 10, 25, 30 is 5. This is another definition. This is also definition of GCD. There is a 2-mark problem. Definitely they will ask a 2-mark problem. Let A and B positive integers with the following canonical decomposition. A has a canonical decomposition. Canonical decomposition means A can be represented as a product of prime number. The prime numbers in ascending order. Similarly, B is another integer. B also represented as a product of prime numbers. The prime numbers are in ascending order. Okay, the power A1, A2, An are positive integers. Okay, suppose A and B are 2 positive integers. In the canonical decomposition, how do you find the GCD of A and B? So here there is a prime P1. Here also there is a prime P1. So GCD means you have to choose the minimum of the power. So GCD of A comma B is nothing but P1 power minimum of A1 B1, P2 power minimum of A2 B2, Pn power minimum of A and B, and this is nothing but GCD of A and B whose number in the canonical decomposition, form of canonical decomposition. Okay, we can do one problem. Using the canonical decomposition of 168 and 180, find their GCD. We know that the canonical decomposition of 168 is 2 cube into 3 into 7. That is by L division method, easily you can find this. Similarly, the canonical decomposition of 180 is 2 square into 3 square into 5. By using previous definition, the GCD of 168 and 180 is nothing but 2 power minimum of 3 comma 2, 3 power minimum of 1 comma 2, 5 power minimum of 1 comma 0, because here there is no 5, so I can assume that 5 power 0. So 5 power minimum of 1 comma 0, 7 power minimum of 1 comma 0. So what do you get? 2 power 2, 3 power 1, 5 power 0, 7 power 0. Finally, my GCD is 4 into 3 into 1 into 1, that is 12. GCD of 168 and 80 is the easiest one. Okay, that is a GCD of 168 and 180 is 12. By using find the GCD by using canonical form, easily you can find the GCD. Okay, but larger number, this lengthiest form. Okay, what do you mean by relatively prime? Up to this, we find that we studied what do you mean by prime. Okay, now we are going to see that what do you mean by relatively prime? What do you mean by relative prime? Simply, I can say that relative prime means suppose A and B are relatively prime means whose GCD is 1. That's all. When we say A and B are relatively prime, whose GCD is 1, then we say that is relatively prime. That is definition. Two positive integers A and B that are relatively prime if their GCD is 1. The GCD of two positive integers become 1, then say that both numbers are relatively prime. That is, if A comma B equal to 1, GCD of A comma B is 1, then A and B are relatively prime. For example, 6 and 35 are relatively prime. 6 and 35 are relatively prime because the GCD of 6 and 35 is 1. There is no common factor other than 1. So we can say that 6 and 35 are relatively prime. Similarly, 11 and 24 are relatively prime since the GCD of 11 and 24 is 1. Did you understand what do you mean by relatively prime? Do you have any doubt? Okay. Pairwise relatively prime integer. Pairwise relatively prime integer. We in previous definition, relatively prime number, that is relatively prime in relatively prime numbers. Okay, the previous definition is relatively prime integers. Okay, in that case we choose only two integers. The next is pairwise relatively prime integer. Pairwise relatively prime number means suppose the positive there are n positive integers. Say there are n positive integers a1, a2, an are positive pairwise relatively prime if every pair of integer is a relatively prime. That is, suppose you want to say that there are 5 numbers relatively prime number means pairwise relatively prime number means if we choose any two integer from those 5 integers, the GCD should be 1. In that case only we can say that the 5 numbers are relatively prime numbers. Relatively, not prime numbers, relatively prime. So now see the definition. The positive integer a1 to an, there are n positive integer are pairwise relatively prime if every pair of integer is relatively prime. That is, if we choose any two element from n element, n integers whose GCD is 1 whenever I not equal to j. If we choose 4, 4, definitely it be the GCD is 4. The GCD cannot be 1. So only right GCD of a aj is equal to 1 whenever I not equal to j. If you see the example, you can clear that idea. The integer 8, 15, 49 are pairwise relatively prime. The integers 8, 15, 49 are pairwise relatively prime. Since the GCD of 8, 15 is 1, GCD of 15, 14 is 1, GCD of 8, 14 is 1. Okay. From 3 number, I have 3 possible of choosing 2 elements. So 8, 8, 15, 8, 49, 15, 49. So all the combination, the GCD is 1. Then we say that 8, 15, 49 are pairwise relatively prime. Suppose if I choose 16, if I choose 6, 25, 77, 91 are not pairwise relatively prime. Because if we choose 6 and 25, the GCD is 1. If we choose 6 and 77, definitely the GCD is 1. If we choose 25 and 77, definitely the GCD is 1. But if we choose 6 and 91, definitely the GCD is 1. If you choose 25 and 91, definitely the GCD is 1. But the only one case it fails, that is the four integers are not relatively prime. That one such case is GCD of 77 and 91 is 7. So these four integers are, we can say that they are not pairwise relatively prime. Okay, did you understand? Do you any doubt? Pairwise relatively means suppose they given is n number of primes. From out of n number of them, you have to choose all collection of two integers. Okay, then find the GCD of those two integers. All the GCD value must be 1. Then only I can say that those n primes, n numbers are or n integers are relatively pairwise relatively prime. Okay. Next, what do you mean by linear combination? Linear combination of the integers a and b is the sum of multiples of a and b. Sum of multiples of a and b. That is, a is a number, there is a multiple alpha a. B is a number, there is a multiple beta b. The sum is nothing but linear combination of a and b, where alpha and beta are integers. The linear combination of integer a and b is nothing but whose form is alpha s plus beta b, where alpha and beta are linear, alpha and beta are integers. For example, suppose linear combination of 3 and 7. Linear combination of 3 and 7 is nothing but 2 into 3 plus 5 into 7 is a linear combination of 3 and 7. What is the linear combination? Another linear combination of 3 and 7. Minus 4 into 3 plus 0 into 7 is also a linear combination of 3 and 7. Okay, linear combination is not a unique one. Linear combination means, suppose linear combination of two integer means I have to find the multiple of 3, I have to find the multiple of 7, then add it. That is nothing but linear combination. Here I mentioned that alpha and beta are integer. I didn't say that alpha and beta are past integer. Okay. This is an important 8-mark theorem. Definitely from the theorem you will get one 8-mark, or from by using the theorem you will get the 8-mark. This is most important topic in the, that is a most important theorem in the topic GCD. So this is an important 8-mark theorem, or by using the theorem we have to prove the important 8-mark problem. Okay, that is, the statement is the GCD of first integer a and b is a linear combination of a and b. That means, you know that what do you mean by GCD of a and b. So GCD of a and b is nothing but a number. Okay, so that number, the GCD is a number. That number represented as linear combination of a and b. You know that what do you mean by linear combination a and b. You know that GCD of a and b. So GCD of a and b is nothing but linear combination of a and b. This is an important theorem. So in last, that is a November, December 2019, okay. They asked us, say this is an 8-mark problem, 8-mark theorem. Okay. We will see the proof. In other words, I can represent GCD of a comma b as bracket open bracket a and close bracket open bracket b. Open bracket a, b, and the close bracket. That is, this is represented as a GCD. What is the linear combination of a and b? There exists an integer x naught and y naught such that a comma b is nothing but a x naught plus b y naught. So this is nothing but GCD. This is nothing but linear combination of a and b. Both are equal. Okay, the GCD of first integer a and b is a linear combination of a and b. This is an important 8-mark problem. Okay, I will show only one problem, then I can finish the class. X plus 28 and comma 12. GCD of 28 comma 12 as a linear combination of 28 and 12. By using the previous theorem, I can express the GCD of 28 and 12 as a linear combination of 28 and 12. Okay, solution. First notice that the GCD of 28 comma 12 is nothing but 4. Is it correct? GCD of 28 and 12. Anyone reply me? Do you accept the GCD of 28 comma 12 is 4? Okay, no one
Yes,
will
sir.
be. Okay, good. So now I have to represent 4 is equal to linear combination of 28 and 12. That is, next we need to find the integer alpha and beta such that the linear combination of 20 and 12 is equal to 4. That means alpha into 28 plus beta into 12 is equal to 4. Such definitely such type of alpha and beta exist. Okay. By trial and method, easily you can assume that because 28, this is 28, this is 12, the answer is 4. So definitely I can put alpha equal to 1, beta equal to minus 2. So 28 minus 24 definitely become 4. So by trial and error method, you can easily find alpha is 1, beta is minus 2, it works. Okay, 1 into 28 minus 2 into 12, which is equal to 4. But in all, the smaller number, easily you can check it. But larger number, we go for some other method. That is an 8-mark problem. This is a 2-mark problem. 8-mark problem means suppose here you have 4-digit number, here 4-digit number, x plus GCD of 4-digit number, 4-digit number as a linear combination of them. So this is an 8-mark problem. This is only 2 mark, but here you have 4-digit number. There is a 8-mark problem. For this, we have to use the Euclidean algorithm. I will teach tomorrow. Okay, not tomorrow, Friday. Okay. So if you have any doubt, please ask me. Okay. Try to do the homework problem. At least only 40 members they send the class notes as well as they did the homework problem. Also, I send the solution for that homework problem. Okay. So one more thing. Yesterday I upload the video link. Some of the student ask the permission from your own mail ID. So if you ask the permission from your own mail ID, we cannot give the access. So if you ask the that is you can suppose you want to access the video link from your college mail ID only, you can ask the permission. Okay, did you understand what I said? Some of the student they asking permission for access the video link from your own mail ID. In that case, that is not possible. We cannot give the permission. Only if you ask the permission from your college mail ID, then only we can give the permission to access the video link. Okay. Okay. Thank you, students. We will meet Friday.